Hi everyone, today we're going to talk about the efficiency of the heap. Um, Mainly we're looking at the efficiency of insertion, top, pop, and the heapify, build heap operations. First we start with insertion operations. Since we're going to use array to represent a heap, so inserting an element into the heap is no more than add the element to the last index in the array. If it's not more than the size of the array, then you don't need to resize it. The time complexity is O of 1, which is very minimum. And the second step of insertion is called bubble up, because once you put the the element into the array, this data structure may not be a heap anymore, so you are going to maintain the heap property. So in worst case, you have to bubble this element all the way up through the height of the tree, which is log of n. On average, it takes 2.607 comparisons are needed to get this element into the right place, and involves 1.607 swaps, which translate to linear complexity of O of 1, which is also very fast. And now we're looking at the next operation, which returns the item with the highest priority, which is as simple as linear complexity of O1, which is also very simple. And next we're going to look at the pop operation, which removes one item, which is highest priority. And we are doing this pop operation by overriding the first item in the array with the last item in the array. This costs O1, and then since it will violate the heap property, we are going to bubble down this element from the top of the heap to the bottom, to the right place. So in worst case, bubble down this element takes O of log n, which is the height of the tree, and in worst case, at least we're going to bubble this element the most way down from the top, so it also is some fraction of O of log n. That is also very obvious. And we're finally looking at the efficiency of build heap complexity, which will turn a binary search, complete binary tree to a heap. How much it will take to turn that structure to a heap. Actually, turns out it is O of n, which is linear in this case. And first step, as we remember, is assume this array, unsorted array, is complete binary tree, which takes very minimum of time complexity. The second step is heapify this complete binary tree by bubbling down each non-leaf node, starting from lowest, from the right to the left. The reason we're not considering leaf node is by themselves they are heap. They're just single element, so we do not have to deal with them. And this operation fulfills heap order property requirement. And we're looking at the naive algorithm analysis to and since I said it involves non-leaf nodes, so it takes n divided by 2 of total nodes. And we're going to bubble down from the lowest level, so it will take half of nodes. Each node takes log n in worst case. And we have to consider odd elements in this heap, so we use n divided by 2 times log n, so give us O of n times log n complexity. So in this analysis, we assume the height of each subheap is log n, which is not true in some cases. So that means elements on different levels takes different height. It takes different time complexity for element in different level. So we're going to look at the analysis of this algorithm. So we're looking at, say we take this data structure as example. We define the height of the tree is the longest downward path between that node to the leaf. So we're defining, for example, this root as of height of 3 because it takes 3 edges to the lowest level of leaf, and 80 has height of 2, 30 has height of 1, 100 has height of 0. Because we use this definition of height to estimate how much computational complexity to do bubble down for each element. So here we are trying to record. We're trying to estimate the worst case for the heapify the whole data structure. So here we start from the root, which has height of 3, and at that level the maximum number of nodes is 1, and we look at the next level and we realized the maximum number of nodes is 2. So we keep going and we generalize a relationship between the height of the node and the maximum number of nodes at that height. So we use the height, meaning the number of bubble down operations for each node times the maximum number of nodes at that height. So that becomes the total worst case time complexity of build heap algorithm. So we use this notation to represent the worst case complexity. So it turns out the majority of the summation is geometric sequence. So then we take this formula to calculate the total complexity of this sequence by setting up the first term as a 2, the common ratio is 2 in this case. And then we're summing up, and eventually we're ignoring the lower term, and we keep the highest term n, so we got On for complexity for build heap algorithm. So we realized this algorithm is better than insertion n elements one by one into the heap, so that is good. So we prove the sum of the heights of the all elements to heapify all elements in the complete binary tree is On by algorithm analysis. Then we're going to summarize the complexity, the average case for average case and the worst case. So insertion in average case takes O1, worst case takes the height of tree O log n. And the top is very easy, O1 for average and worst case. And pop, in average case, you have to pop through the part of the height of tree. In worst case, you have to pop this element and bubble down the entire height of this tree. And we just proved that in worst and average case, it takes On to realize the time complexity for building a heap. That's it.